Hi, welcome back to our course on concepts of programming languages. Today we will look at types, or the first part of types. Since types is a rather sophisticated, complicated topic, we will be splitting this into two short sessions so that you can assimilate the ideas presented in each topic, each session. So roughly today, this is our agenda. We will introduce types. We will look at different kinds of types, or rather types of types, primitive types, product types, container types, and enumeration types. And finally, in today's session, we will look at the difference between strong and weak typing, and then also the difference between static and dynamic typing, and briefly look at the advantages and disadvantages of each form of typing. Okay. So essentially, types are used by language designers to essentially, they are looked at from two perspectives by language designers. One is the implementation perspective, which says what kind of data representation and storage you want for variables. The other is the logical or the mathematical perspective, where language designers try to codify properties of the kinds of values that go inside each type. Right? Typically, when language designers are designing types for their language, what kind of types they want to support for their language, they look at both of these perspectives parallelly. Right? Okay. So generally, types are contracts that define variables or that bind variables to what variables that bind variables to what we can do with them and what they can be. If, for example, if you know that a variable v here can only hold a type where the values are only up to 127, then you can use that to efficiently implement it based on what kind of memory is provided by the machine language that you're translating it to. And types also, as mentioned before, provide ways to mathematically prove or disprove certain properties that hold to a particular variable. Right. So the first kind of types are the primitive types. Primitive types are they are the basic building blocks of any kind of data that can be used in your programming language. Generally, they are built in, meaning your language provides support for them. By design, but they can also be provided in the form of libraries that you have to import and use. Right. Some examples of primitive types are Boolean types, which can either represent true or false. These represent data where you want to perform some checks on whether a particular property is true or not. Integral types refer to natural numbers. They can be signed or unsigned. Floating point types, which refer to real numbers or even complex numbers. And so there are many other primitive types that are supported. An interesting primitive type is also something that most of you must already know about, which is called a unit type, which is essentially void in many of the languages that we know. Essentially, this is a type of variable that holds nothing. Right? Okay. So another type of type is ordinal types. Ordinal types are types where the values can map to natural numbers one-to-one. There are advantages for this kind of mapping because processing them in your machine and performing optimizations become much easier. So examples of ordinal types are integers that we saw. Booleans can also be mapped to ordinal numbers. Essentially, they can be mapped to either 0 or 1. Character types are examples of ordinal types, and enumerations, all of these types we will look at in a little bit more detail in the upcoming slides. So, integral types. Integral types are essentially refer to natural numbers, or are types of data where the data can be natural numbers. The amount of numbers that can be represented are either sometimes determined by the machine itself. If your machine supports 8-bit, 64-bit, 32-bit, this decides how much integers are supported by your integral types in your language. They can be, as mentioned, signed or unsigned, referring to positive or negative integers. They can be big numbers, meaning they can be unlimited. They can be of unlimited size, and this would require your language to perform complex representations in the form of lists or something like this internally to be able to support such unlimited big integers. Some other types of integrals are also decimal integers, where you say, hey, I want to support, my language supports integers with 10 decimal digits or 20 decimal digits and so on and so forth. You can also have integer types that are bounded by a particular range. You can say my value is of integer type, but the variable can only contain values from m to n, meaning m plus 1, m plus 2, so on and so forth to n. Right? These are various kinds of integral types that are supported by languages and that you can create for your own purpose in your languages. The other kind of numeric types are real or complex numbers. Essentially, these are represented as floating point numbers because they allow high performance computing to be performed easily, but this also means that it requires hardware support. It's called floating point representation because you can essentially float the decimal point to the left or right and compensate it by multiplying it with an exponent, as it is shown here. The number 1.235 is essentially 1, 2, 3, 4, 5, which is the significant, or in some terminology it's called the mantissa, multiplied by the base, in our case it is 10, to the power of the exponent, which is -4 here. So essentially you can create any real number using this format, significant or mantissa multiplied by base to the power of exponent. Right. I'm not going to go into the details of all kinds of fixed point numbers that are supported, but all kinds of real numbers that your language can support. But on a high level, they can have, of course, they can also be fixed point, they can also be big rational numbers or decimal reals. And C99, for example, also supports complex numbers. Right? Okay, the other kind of primitive type, or the final kind of primitive type that we will look at today, are characters. Characters essentially are, again, ordinal types. They represent readable characters, which are alphabets, for example, in your language. In most modern languages, they map to integrals. Right? In some languages, they are also provided inherently. There are two kinds of characters that are supported. The simpler kinds, which have the ASCII representation, they support 127 different characters, and they can be represented with 1 byte or simply even 7 bits. Right? The other variant of character types are Unicode types. These essentially the difference is that they are stored in 32 bits, meaning they can store a lot more kinds of characters. As you can see here, here we have an example of the a umlaut from German-like languages, which has a different encoding. Then there is Chinese characters, which have other encodings, and so on and so forth, even hieroglyphics. So the idea here is that if you support character types which are Unicode, you can support a lot more readable characters. Right? Okay, so another type, strings, which can be primitive depending on the language you look at. They're essentially sequence of characters. Right? The representation here varies based on your language. Strings generally have a fixed number of characters and they end at a particular point. Where it ends, it depends on the representation your language supports. So for example, if the first kind of representation variant is using the length prefix, essentially the prefix of your string says how much characters will follow. This will make sure when you're reading the string, or when you're reading or writing to the string, you are not writing to a part of the string that does not belong to its length. C-like languages also follow the idea of using a terminator character, where you have a string of finite length, and then the end of the string is determined simply by a terminator character. C, for example, uses 0, 0. Now let's look at some little bit more interesting type of types. First of them are product types. Product types essentially allow you to group data of different types together. These can be useful, for example, when you want to have a data type that combines real and a string together. This might be useful, for example, when you want a type that describes both an object and the price of the object. Here, for example, an instance of the type would be chair, 23.56, which is the price of the chair here. Right? So product types are generally represented formally using the into symbol, or the multiplier, the x symbol, which will also be useful when we are defining function types, which we will see later. So product types come in two variants, tuples and records. Tuples also allow, as mentioned before, they provide mechanisms to group types together. Tuples follow the positional grouping, meaning you refer to each variable inside the tuple. Tuple can be of any number of tuple can be of any size, right? So they can have 2, 3, 5 elements that are combined together, and they can all have different types. And yes, so essentially referring to them or indexing them is done using the position of it. Some languages start their position with 1, some languages start their positions with 2. As mentioned before, each element or field of a tuple can be of a different type. Languages which have inbuilt support for tuples are, for example, Haskell, Python, etc. Python being the most popular, right? So those of you who have used Python must have definitely already used tuples in your computations. So common operations that are supported by tuples are subscription, meaning ways to read read values out of these tuples. So here you would just use the subscript saying, hey, I want the second, or in this case the third element, and I want you to check is the third element of this instance of the tuple called tuple x is equal to 23, right? Some languages like Haskell use the deconstruction, meaning you can match your tuple to a particular pattern. For example, here you would match the values of your tuple to id, name, b, and then you can essentially get the second entry in this tuple simply by the name, which is the pattern you've matched to the second entry of the variable. In memory, typically tuples are stored adjacently. This is for efficient processing, but some languages also have ad hoc way of storing and retrieving tuples. So the other kind of product types are records. Records are similar to tuples, but instead of grouping these types by positions, here they are grouped by names, right? So again, records can also have each element or field of this record maybe of a different type. I'm sorry, I've written tuple here, but it's a record. But each element and field must have a distinct name. You must have seen versions of records. Structs are versions of records. Most languages support some form of records, and even inside memory they are stored typically adjacently. But what is stored adjacent to what depends on the language itself. C, C++, for example, store these types next to each other as they are declared. So if you have a struct where the first variable is an int, second variable is a string or char, the string, the int would come first in memory, and then the string would, the character would be next. ML, for example, stores them in alphabetical order. So if you have an int x and char y, int x and char a, the character would be stored first, and then the int would be stored next. So these are language decisions. These are design decisions that languages have taken on how to store variables of record type. Operations you can do, as we've seen before, subscription to access values of record type. Here subscription would use typically the dot notation is used, and then after the dot follows the name of the particular entry inside your record that you want to access. So here t.name would get the entry inside your record named name, right? So another interesting type are container types. Containers allow you to store multiple elements of same or similar types together. Examples of these that most of you must have already used are, for example, lists or dictionary lists, or list of values, dictionary store, associative values together. We'll see examples of those, and also sets are examples of container types. So we'll look at the first kind of container type, which are arrays here. Arrays essentially are types of multiple, or essentially refer to multiple elements of the same type, right? Here is an example byte array in Java. you would have to specify the length of the array itself in some form. Some languages allow you to not specify a length, but this has to, the length of it is important so that you don't access elements outside the array without proper access to them. So Java, for example, inside memory first stores the length of the array, followed by the array itself, the values of the array one by one itself, right? So another variant of array is multidimensional array. These essentially allow you to have arrays of arrays, or matrix, right? So these are very important for performing in these in modern times machine learning computations. So here is an example of a multidimensional array described in C. You have a matrix of dimension 2 cross 2, meaning you will have two arrays each containing two values, or in the metric representation you have a matrix of two rows and two columns, and you use subscription to access them. So if you say matrix of 1, 0, it would access the second row and the first row and second column's value, right? How these multi-dimensional arrays are stored in memory depends on the language itself. C and C++, for example, follows the row major way of storing the values, for which means that it would store in your memory for the contiguous locations. First, the values of the first row are stored, then the second row, then the third row, and so on and so forth. For example, the matrix that we've shown above will be stored by C++ as 11, 12, which is the first row, then 13, 14. Languages like Fortran follow column major representations, which is essentially the transpose of the row major. So it would store the first column, which would be 11 and 13, followed by 12 and 14, which would be the second column. Languages like Java use what is called a jagged representation. They call it jagged because the size of the individual arrays can be different from okay, so for that first I need to describe how a jagged array looks in memory. So jagged arrays are essentially arrays which have first, as mentioned before, as I showed before in Java, which would have the number of elements that are in this array, and each array will be a reference to another array. So here, for example, each array represents each row in your matrix itself, right? So they are called jagged because the size of these individual arrays may be different from the size of the top level array that is referring these arrays, right? Okay, so another form of arrays are associative arrays, or as most of you know, they are dictionaries or maps or are hashes. Essentially, associative arrays associate a key to a value, right? Sets are also kind of associative arrays, but just have values. They don't have keys. But I'll leave this. Generally, the way to access associative arrays is essentially to say, hey, so-and-so array, get me the value of this key, right? This is the way you can access, most languages provide access to associative arrays, right? Okay. So enumeration types allow you to define your type with a list or enumerated list of values. Essentially, for example, here you have two enumerations, type weekday, which contains the values Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. This means that anytime you instantiate a variable of type weekday, that variable can have only one of these 7 values. Booleans can be considered a variant of enumerations where you have only two values, either false or true, right? So enumerations can also be thought of as ordinal types because you can map the values to natural numbers 0 to n minus 1, n being the size of the enumeration that you're supporting. So another variant of types are called sum types. Sum types essentially allow you to say that my type is one of these A, B, C options of types. Here is an example of a function, get next event. What do you think is the return type of get next event? For that, let's look at the code. Inside get next event, if the key is pressed, then it returns the character that was read, which means it's returning a character. If the next event is actually a movement of the mouse, then it's going to return the position of your mouse or the coordinates of your mouse pointer, which would be a product type of int cross int. Or if nothing happens, it's a boolean that is being returned, right? So the return type of this get next event is a summation of either a character or int cross int or boolean. This is what is called a sum type. When the type of your variable or your function is one of many, or has to represent one of many. An example of sum types are actually unions in C. Some of you may have already used them. The advantage of unions are that they allow the variables inside to share the same location, right? Because you want to only use one or the other, right? For example, here is a union U, which has two types. One is an int or a float, right? But the danger with union types in C is that unions in C are not type safe. To see what I mean, let's go further into our example where you have a u.I which is assigned to 1. And then when you try to access u.x, you will still get it because the values of u, the I and x share the same memory location. In order to mitigate this issue, there's a variant of unions called discriminated unions or tagged unions. To understand what tagged unions or discriminated unions are, let's look at an example of a discriminated union type from Ada. Here you are defining a type event type, and then what the event type represents depends on the tag here, the kind, right? So if the kind is a key, then you would return a key character, which is a character. If your kind is mouse, then you would define a product type x comma y. X and y both are integers. If your kind is nothing, then your type is null, right? In memory, for discriminated unions, the tags get a dedicated memory location. Here kind would get a dedicated memory location for your event type, and depending on the value, the memory location for the values themselves are shared. But this is still type safe because your compiler can check the values for their types based on the tag, in this case, which is kind. Another variant of union or discriminated union types are algebraic types, which are supported by languages like Haskell, where you can use the pipe operation to essentially say, but my type is one of these types, right? So, but the nice thing about algebraic types are also that you can recursively use them to get combinations of your supertype, which is, you can say that my event, the type event, is any combination of events inside, right? So the other kind of important types that we will see today are reference types. Reference types are something that most of you must have used, and we have already seen the pros and cons of having references and references in the previous sessions. But let's get a brief overview on what are the pros and cons and the various subtleties that go into designing reference types. So essentially, reference types are types of values that can be updated, meaning these variables are mutable. You can update them, you can change the values of these types. Most languages allow mutability in some form or the other. Let's look at an example from Pascal. Here you have a variable x or a reference variable x of types reference variable, which has which points to a memory location which has the value 1. You print it, it prints 1. Once you have updated it with 2, the memory location that is pointed to by x is changed to 2. So when you print x, it prints 2. The advantages of reference types are that they allow efficient reuse of existing storage. You can use the same memory location to store different values of different points of time. They also allow you to modify behavior of your program through updates. So your program behaves a certain way when the value 1 is passed, it behaves another way when the value 2 is passed. You can trigger these alternative behaviors simply by providing updates. All right? to the same storage, to the value referred by the same storage. The disadvantages of reference types are that they have complex semantics. A couple of examples of those. If you remember from the operational semantics session, we looked at what is a program store, which is updated, and you need to constantly have a history of your store to decide what behavior a program has, right? And evaluation order becomes very important. If you have reference types, recall the session on referential transparency, and yeah, you would need to consider these factors if your language supports reference types, right? Here is another example of reference types. Here are some basic properties of reference types, which we already saw in the previous slides in the previous sessions, but essentially reference types support mutable variables. Almost all languages support reference types in some form or the other. It is implicit in certain imperative languages. Basic operations that are supported are updates or assignments, which essentially take the form r equal to value, which updates the value at that particular memory location pointed to by the reference variable r. Reading is usually implicit. Most languages don't expect you to do any specific kind of reading of these reference variables. You just simply use the name of the reference variable and you get access to the value that is stored in the memory location pointed to by the reference variable, right? One interesting thing to consider is what happens when you have nested scopes and you reassign reference variables or update reference variables, right? So in order to understand that, let's look at a couple of examples, one on the left hand side, one on the right hand side. On the left hand side, you have a reference variable x, which has the value 1, and if you update it to the value 2, and if you print x inside the scope where the value is updated, and if you print it outside, the value is still going to be the same, because you have updated. There is only one version of x and it is pointing to one memory location and you modified the value there. But the other version is rebinding. So here you have a variable x which is updated to, which is initialized with the value 1, but you're entering a new scope where you have a nested scope where you have updated x with the value 2. But since you have gone inside a new scope, depending on the language, what can happen is you have two different copies of x. One x in the broader scope, one x in the nested scope, and then you have two different prints. So this would essentially print 2 when it's inside the scope where the value of x is 2, because it's pointing to another x, and then when it comes out of the scope, it's going to print the outer print int will see the older binding, which would print the value 1, right? The last kind of types that we will see today are function types. Function types are essentially types that you associate with functions themselves, right? If you recall from the previous session on functional abstractions, functions have parameters and functions have return value. So essentially, a type of a function is a combination of the parameters and then the type of the return value, which is separated by the arrow mark. So, and then you use the cross notation to specify that the type of the parameter is the product of the various types inside the function themselves. So here you have a function int multiply, which takes in two parameters of types integer and integer. So the type of this function would be int cross x arrow mark int, which is the return value, right? Let's look at a brief very high level semantics of how to apply functions. If you have a function of type t1 returns t2, and if the type of some expression a is t1, then applying f on a would, or the type of applying f on a would be t2. We'll see a lot more details of how we will use the function application rule when we are looking at type checking and type inference. And finally, another variant of function types are when you have functions which have nested functions defined inside them. Essentially, I'll tell you why this is relevant. Let's take an example here, function f, which takes in two parameters, int, and it returns an int. Essentially, it's f sums up a and b. But another way of defining the function f is also to use closures or nested functions, similar to what we saw in the last session on function abstractions. So here you have a function g, which takes in an integer and then returns an integer, but g itself defines inside its own scope another function g2, which has access to the value a from the top level function, but it takes in one integer and again returns an integer, but it uses the values passed on by the top level function. Essentially, g returns g2, right? The type of f that we saw as before is simple. It's int cross s, int cross int, arrow mar, arrow int. But the type of g itself is int, and it returns a function which takes in an int and returns an int. This is called currying. Generally you can translate the times operator or the cross operator and convert it into an arrow, and this has various applications. I will not go into the details of them in this session. Finally, now that we've seen different kinds of types, let's look at what is type safety and strong typing. Essentially, the definition I've written down here. A language is strongly typed if every value inside a program of that language has a type, and any type error can be detected before the code containing the error is executed. All right, so various languages have different levels of type safety. Java, Python, modern languages are strongly typed. This is important because you can perform checks, analysis, and verification on your program. C and C++ are weakly typed, and assembly languages are not typed at all, meaning values don't have type, and essentially verifying properties on programs in assembly is pretty much impossible, right? So strong typing can happen in two forms. It can happen as static typing, or it can happen as dynamic typing. Static typing essentially means that I look at my code and I'm going to check if every assignment or read or access to a variable type checks. Here is an example. You have a variable of type variable x of type int, and then you're trying to store a string into it. This would immediately throw a type error. Languages like Java, Haskell, C, C# have static typing, but we'll see in the next slide something interesting about languages like Java. But this is static typing. Dynamic typing checks for the same kind of errors, but it does those only when the code containing the type check is actually executed, right? So here also you would get a type error, but only if the code containing x equal to string is executed in some fashion, right, or called in some fashion. Now languages like Python, Ruby, and Perl support dynamic typing, but some languages support both static and dynamic depending on the context. If you recollect from the previous slide, I mentioned something interesting about Java. Java and C# are one of those interesting or some of those interesting languages that support both static and dynamic typing depending on the context themselves, right? Overall, this is a comparison of the advantages and disadvantages of different kinds of typing. If you have no typing at all, type errors can't be detected, but on the plus side, it requires no runtime support. If you have weak typing, well, values do have types, but only some of the type errors are detected. But again, the advantage is that your language does not have to do any runtime magic. And within strong typing, if you have dynamic typing, you can both with static and dynamic typing, you can have values of all values of types, and all kinds of type errors are detected. But with dynamic typing, you require some kind of runtime support, which is generally trade-off that you want to do when you want your results to be much more accurate and much more precise. So with that, we come to the end of today's session. We looked at the basics of types, various kinds of types, and then we also looked at the different kinds of typing. In the next session, we will continue discussing types, but we will look at type checking and type inference. Thank you.